let's build a machine learning model. So probably go this way, build a machine learning model, resume the path. Now, I want to go back to the one before because I like this image. So, introduction to machine learning. The year is 2049. New York is overrun by bots and web crawlers. The capabilities of machine learning have reached new heights, and the world as we know it will never be the same. Facial recognition technology that helps users tag and share photos of friends can now tag future friends. Night drones are on the prowl. Machine learning powered self-driving cars and flying cars are now massively available to consumers. The steering wheel has become a thing of the past. Recommendation engines that suggest what VR shows to watch and what products to buy will now display a different environment for each user group. At the dawn of a new age, you can't help but wonder, what is machine learning and how did it pivot our world so drastically? In this lesson, you will get an introduction to this discipline of computer science that enabled these new technology advances. What is machine learning? While at IBM, Arthur Samuel developed a program that learned how to play checkers, 1959. He called it the field of study that gives computers the ability to learn without being explicitly programmed. What does that mean? As programmers, we often approach problems in methodical, logic-based way. We try to determine what our desired output should be, and then create the proper rules that will transform our inputs into those outputs. Machine learning flips the script. We want the program itself to learn the rules that describe our data the best by finding patterns in what we know and applying those patterns to what we don't know. These algorithms are able to learn. Their performance gets better and better with each iteration as it uncovers more hidden trends in the data. Take a look at the timeline on the right. Since Mr. Samuel's usage of the term, we've made astonishing advances in the field. So, in 1950, Alan Turing publishes Computing Machinery and Intelligence. In 1957, we get the perceptron algorithm. In 1967, K nearest neighbors algorithm. In the first AI winter, the fear of AI and lack of computing resources lead to fewer developments in the field. In 1985, we get speech recognition. In the second AI winter, again, fear of AI and lack of computing resources lead to fewer developments in the field. In 1998, MNIST handwriting recognition. In 2003, Bengio et al. Published a neuroprobabilistic language model. In 2006, ImageNet visual recognition dataset is created. In 2011, IBM Watson beats humans at Jeopardy. In 2012, AlexNet wins the ImageNet challenge. In 2014, DeepFace facial recognition. 2016, AlphaGo beats humans at Go. 2018, GPT-1 is released, and subsequently, the AI boom begins with ChatGPT, Llama, DALL-E, Claude, Bard, Stable Diffusion, and more. Supervised learning. Machine learning can be branched out into the following categories: supervised learning, unsupervised learning. Supervised learning is where the data is labeled and the program learns to predict the output from the input data. For instance, a supervised learning algorithm for credit card fraud detection would take as input a set of recorded transactions. For each transaction, the program would predict if it is fraudulent or not. Supervised learning problems can be further grouped into regression and classification problems. Regression. In regression problems, we are trying to predict a continuous valued output. Examples are, what is the housing price in New York? What is the value of cryptocurrencies? Again, regression problems, we're trying to predict a continuous valued output. Classification. In classification problems, we are trying to predict a discrete number of values. Examples are, is this picture of a human or a picture of an AI? Is this email spam? For a quick preview, we will show you an example of supervised learning. NYBD, New York Bot Department, wants to analyze how New Yorkers are talking to one another so that they can determine who is being negative. They have built a naive Bayes classifier that predicts whether an intercepted text is good or bad, based on the frequency that a word is used in a good training example or a bad one. Run the code to see if the model classifies the sentence, "This hot dog is awful," as a negative negative sentiment. This text is negative. The NYBD wants to know what its citizens are saying. Put in the sentence, I love my government in intercepted text and see if the classifier predicts a positive sentiment. This text is positive. Put a sentence of your own in intercepted text. I hate to love, to hate, to love my government. This text is positive. What if we change it to I hate to hate? That's still positive. What about I hate to hate to hate? This text is negative. Let's keep going. Unsupervised learning. Unsupervised learning is a type of machine learning where the program learns the inherent structure of the data based on unlabeled examples. Clustering is a common unsupervised machine learning approach that finds patterns and structures in unlabeled data by grouping them into clusters. Some examples: social networks clustering topics in their newsfeed, consumer sites clustering users for recommendations, search engines to group similar objects in one cluster. For a quick preview, we will show you an example of unsupervised learning. NYBD wants to determine how humans and cyborgs differ from each other in terms of the speed of recovering from wounds, emotional intelligence, EQ, words per minute, WPM, reading speed. They have taken measurements of these things for the New York population and have plotted them on 3 axes. Press run to see the clusters. These are the clusters. So over here at Time to Heal, us humans, we're doing pretty good. In terms of EQ, actually, us humans are actually doing the worst, huh? I guess robots heal faster. Reading speed. This 3D graph is, can I move it? A little bit confused about the z-axis, but regardless, we see clusters are importing Codecademy lib3 Seaborn, matplotlib for the plot, numpy's np from os.path, import join dir name appspace from mpl toolkits. So this is mainly a SciKit learn cluster. We're doing k-means. We're importing a data set from SciKit learn. It's the iris equals datasets.load iris. X equals iris.data, y equals iris.target. Fig num equals 1, plot the ground truth. Fig equals plt.figure, fig num, fig size. AX, axes 3D for name label in robot 0, cyborgs 1, humans 2. AX.text 3D, and so on. Let's keep it going. Begin your journey. Ding, ding, ding. It was but a dream and there's still time. Understanding machine learning will help you change this bleak future or be ready for it. As you begin your journey through our machine learning curriculum, you will learn the different applications of this powerful field. You will begin your own models. You will build your own models, test them, and try to improve them. You will analyze bigger and more complex data and deliver faster, more accurate results, even on a very large scale, using supervised learning and unsupervised learning. Throughout your exploration of ML, we hope you gain an understanding of how to harness predictive models to do good and enhance human life rather than replace it. So what are you going to build? What is the kind of future that you want to see? Very inspiring. Good job, Codecademy. The machine learning process. Learn the general structure of how to approach machine learning problems in a methodical way. The process. When people think of machine learning, they often think of a program that is taking in data and spitting out predictions and insights. The process of performing machine learning often requires many more steps before and after the predictive analytics. We try to think of the machine learning process as 1, formulating a question, 2, finding and understanding the data, 3, cleaning the data and feature engineering, 4, choosing a model, 5, tuning and evaluating, and 6, using the model and presenting results. 1, formulating a question. What is it that we want to find out? How will we reach the success criteria that we set? Let's say we are performing machine learning for a high traffic fast casual restaurant chain, and our goal is to improve the customer experience. We can serve this goal in many ways. When we're thinking about creating a model, we have to narrow down to one measurable, specific task. For example, we might say we want to predict the wait times for customers' food orders within 2 minutes so that we can give them an accurate time estimate. 2. Finding and understanding the data. Arguably, the largest chunk of time in any machine learning process is finding the relevant data to help answer your question and getting it into the format necessary for performing predictive analysis. We know that for supervised learning, we need labeled datasets, or datasets that have clear labels of what their ground truth is. For an example like the restaurant wait time, this would mean we would need many examples of past orders tagged with how long the wait time was. Maybe the restaurant already tracks this data, but we might need to augment the data collection with a timer that starts when the customer orders, stops when the customer receives their food, and records that information. Creating the system of recording data, as well as gathering enough data to be able to train our model, will take time. Once you have your data, you want to understand it so that you will know what model to apply and what the outputs will mean. First, you will want to examine the summary statistics, calculate means and medians to understand the distribution, calculate percentiles, find correlations that indicate relationships. You may also want to visualize the data, perhaps using box plots to identify outliers, histograms to show the basic structure of the data, and scatter plots to examine relationships between variables. Let's say we're examining the existing distribution of wait times. We see that the overall average is 6.25 minutes per order, but we also produce this histogram with the wait on the x-axis in minutes and the number of orders on the y-axis in orders. We might glean from this there are two main groups of orders. One group seems to cluster around 4 minutes, while another smaller group seems to cluster around 11 minutes. We could use this to modify our question and build a model that will classify whether or not an order will be in this short time frame or in the long time frame. Is it dependent on the food that it ordered, the time of day of the order? Perhaps we just become aware of the bimodality of our data. If our model consistently predicts a wait time of around 6 or 7 minutes, then we are not taking into account the true structure of our data. 3. Cleaning the data and feature engineering. Real data is messy. Data may have errors. Some columns may be empty. The features we're interested in might require string manipulation to extract. Cleaning the data refers to the process by which we address missing values and outliers, among other things that may affect our insights. We may see that we have a group of orders that took over 20 minutes due to an emergency in the kitchen one afternoon. This is pushing our average wait time up and may skew our predictions. If we want to model the more general functioning of the restaurant, we may want to remove these values. Feature engineering refers to the process by which we choose the important features or columns to look at and make the appropriate transformations to prepare our data for our model. We might try normalizing or standardizing the data, augmenting the data by adding new columns, removing unnecessary columns. After we test our model and the data we have, we might go back and re-engineer features to see if we get a better result. 4. Choosing a model. Once we understand our data set and know the problem we are trying to solve, we can begin to choose a model that will help us tackle our problem. If we are attempting to find a continuous output, like predicting the number of minutes someone should wait for their order, we would use a regression algorithm. If we are attempting to classify an input, like determining if an order will take under 5 minutes or over 10 minutes, then we would use a classification algorithm. Different classification and regression algorithms work better on different types of data sets. We use different models on categorical and numerical data, and different models on data sets with many features and data sets with few features. Our models also have different levels of interpretability. How easy is it for us to see what these results mean and what led to them? When we teach the models, we will discuss the trade-offs of using each one. 5. Tuning and evaluating. We often want to set a metric of success so that we know the model we've chosen is good enough. Are we looking for accuracy, precision, some combination of the two? We discussed this in our lesson on precision and accuracy. Each model has a variety of parameters that can change how it makes decisions. We can adjust these and compare the chosen evaluation metrics of the different variants to find the most accurate model. For example, let's say we're using a k-nearest neighbors regression algorithm to solve the wait time prediction problem. This algorithm uses a parameter k, which you will learn about in the KNN lesson, or k-nearest neighbors lesson. We can adjust k to get different results. I didn't fully consume that information. So again, 5, tuning and evaluating. We often want to set a metric of success so that we know the model we've chosen is good enough. Are we looking for accuracy, precision, some combination of the two? We discussed this in our lesson on precision and accuracy. Each model has a variety of parameters that change how it makes decisions. We can adjust these and compare the chosen evaluation metrics of the different variants to find the most accurate model. For example, let's say we're using a k-nearest neighbors regression algorithm to solve the wait time prediction problem. This algorithm uses a parameter k, which we'll learn about in the KNN lesson. We can adjust k to get different results. Is it ideal to compare against 3 nearest neighbors, 10, 1? We can try many different values of k and see which one gives us the highest level of accuracy. From this analysis, we would set our k to be 26, which got the highest level of accuracy. Using the model and presenting results. Step 6. When you achieve the level of accuracy you want on your training set, you can use the model on your data, on the data you actually care about analyzing. For our example, we can now start inputting new orders. The input could be an order with features like the type of item ordered, the quantity, the time of day, the number of employees working. The output would be how long the order is expected to take. This information could be displayed to users. An important step is being able to convey what you've learned and created so that people can use it in the future. Sometimes you learn more about your data by looking at the model. For example, using multiple learning regression can give you insights into the importance of each feature. We can create a feature importance graph to visualize this for those unfamiliar with our model. So our feature importance graph shows the type of item ordered, the time of day, the quantity, the number of employees working, and the number of modifications. And these are ranked by importance, and clearly the type of item ordered is the most important, whereas the number of modifications is the least important. Time of day is also very important. Number of employees working isn't as important. So anyway, your process. The process we have outlined is a fairly standard process for performing machine learning. As you get experience going through this process on your own, with your own problems, you will start to form your own process. The steps may not be linear. As you clean your data, you may uncover a better question to ask. As you tune your model, you may realize you need more data and go back to the collection step. The important part is to stay curious and to keep iterating until you find a model that works the best. Supervised versus unsupervised. Introduction to the two main classes of algorithms in machine learning, supervised learning and unsupervised learning. As humans, we have many different ways we learn things. The way you learned calculus, for example, is probably not the same way you learned to stack blocks. The way you learned the alphabet is probably wildly different from the way you learned how to tell if objects are approaching you or going away from you. The latter you might not even realize you learned at all. Similarly, when we think about making programs that can learn, we have to think about these programs learning in different ways. Two main ways that we can approach machine learning are supervised learning and unsupervised learning. Both are useful for different situations or kinds of data available. Supervised learning. Let's imagine you're first learning about different genres in music. Your music teacher plays you an indie rock song and says, "This is an indie rock song." Then they play you a K-pop song and tell you, "This is a K-pop song." Then they play you a techno track and say, "This is techno." You go through many examples of these genres. The next time you're listening to the radio and you hear techno, you may think, "This is similar to the 5 techno tracks I heard in class today. This must be techno." Even though the teacher didn't tell you about this techno track, she gave you enough examples of songs that were techno so you could recognize more examples of it. When we explicitly tell a program what we expect the output to be and let it learn the rules that produce expected outputs from given inputs, we are performing supervised learning. A common example of this is image classification. Often we want to build systems that will be able to describe a picture. To do this, we normally show a program thousands of examples of pictures with labels that describe them. During this process, the program adjusts its internal parameters. Then, when we show it a new example of a photo with an unknown description, it should be able to produce a reasonable description of the photo. When you complete a CAPTCHA and identify the images that have cars, you're labeling images. A supervised machine learning algorithm can now use those pictures that you've tagged to make its car image predictor more accurate. Unsupervised learning. Let's say you are an alien who has been observing the meals people eat. You've embedded yourself into the body of an employee at a typical tech startup and you see people eating breakfasts, lunches, and snacks. Over the course of a couple of weeks, you surmise that for breakfast, people mostly eat foods like cereals, bagels, granola bars. Lunch is usually a combination of some sort of vegetable, some sort of protein, some sort of grain. Snacks are usually a piece of fruit or a handful of nuts. No one explicitly told you what kinds of foods go with each meal, but you learn from natural observation and put the patterns together. In unsupervised learning, we don't tell the program anything about what we expect the output to be. The program itself analyzes the data it encounters and tries to pick out patterns and group the data in meaningful ways. An example of this includes clustering to create segments in a business's user population. In this case, an unsupervised learning algorithm would probably create groups or clusters based on parameters that a human may not even consider. Summary: we've gone over the difference between supervised and unsupervised learning. Supervised learning, data is labeled, and the program learns to predict the output from the input data. Unsupervised learning, data is unlabeled, and the program learns to recognize the inherent structure in the input data. What is SciKit Learn? Open source machine learning library for Python, built on NumPy, SciPy, and Matplotlib. In this course, we will learn how to construct various machine learning algorithms from scratch. In the real world, however, we don't want to recreate a complex algorithm every time we want to use it. Writing an algorithm from scratch is a great way to understand the fundamental principles of why it works, but we may not get the efficiency or reliability we need. SciKit Learn is a library in Python that provides many unsupervised and supervised learning algorithms. It's built upon some of the technology you might already be familiar with, like NumPy, Pandas, and Matplotlib. The functionality that SciKit Learn provides include regression, including linear and logistic regression, classification, including k-nearest neighbors, clustering, including k-means and k-means plus, model selection, pre-processing, including min-max normalization. As you move through Codecademy's machine learning content, you will become familiar with many of these terms. You will also see SciKit Learn and Python sklearn modules being used. For example, sklearn.linearmodel.linear regression is a linear regression model inside the linear model module of sklearn. The power of SciKit Learn will greatly aid in your creation of robust machine learning programs. Happy coding. Regression versus classification. Learn about the two types of supervised learning algorithms. Machine learning is a set of many different techniques that are each suited to answering different types of questions. One way of categorizing machine learning algorithms is by using the kind of output they produce. In terms of output, two main types of machine learning models exist: those for regression and those for classification. Regression. Regression is used to predict outputs that are continuous. The outputs are quantities that can be flexibly determined based on the inputs of the model rather than being confined to a set of possible labels. For example, predict the height of a potted plant from the amount of rainfall. Predict salary based on someone's age and availability of high-speed internet. Predict a car's MPG, miles per gallon, based on size and model year. Linear regression is the most popular regression algorithm. It is often underrated because of its relative simplicity. In a business setting, it could be used to predict the likelihood that a customer will churn or the revenue a customer will generate. More complex models may fit this data better at the cost of losing simplicity. Classification. Classification is used to predict a discrete label. The outputs fall under a finite set of possible outcomes. Many situations have only two possible outcomes. This is called binary classification: true or false, 0 or 1, hot dog or not hot dog. For example, predict whether an email is spam or not, predict whether it will rain or not, predict whether a user is a power user or a casual user. There are also two other common types of classification: multi-class classification and multi-label classification. Multi-class classification has the same idea behind binary classification, except instead of two possible outcomes, there are three or more. For example, predict whether a photo contains a pear, apple, or peach. Predict what letter of the alphabet a handwritten character is. Predict whether a piece of fruit is small, medium, or large. An important note about binary and multi-class classification is that in both, each outcome has one specific label. However, in multi-label classification, there are multiple possible labels for each outcome. This is useful for customer segmentation, image categorization, and sentiment analysis for understanding text. To perform these classifications, we use models like naive Bayes, k-nearest neighbors, SVMs, as well as various deep learning models. An example of multi-label classification is shown below. Here, a cat and a bird are both identified in a photo, showing a classification model with more than one label as a result. Choosing a model is a critical step in the machine learning process. It is important that the model fits the question at hand. When you choose the right model, you are already one step closer to getting meaningful and interesting results. Measuring model accuracy, distance formulas. Learn about the role of distance functions in machine learning. Machine learning is often used to predict numeric values. For example, economic models might try to forecast stock prices, and weather models might try to predict the temperature on a specific day. Because these models can be incredibly influential, understanding how accurate they are is crucial. We need to know how far off the model's predictions are from the actual values. This is where the mathematical concept of distance comes into play, offering a quantitative measure of a model's accuracy. Different kinds of distance. Measuring distance may seem completely straightforward, but in practice there are actually many different kinds of distance. As an example, take the problem of measuring the distance it takes to travel between two places in a city. If we happen to have a helicopter, the shortest distance might just be the length of a straight line from point A to point B. But if we're walking, now the shortest distance has to take the structure of city blocks and buildings into account. Unless we have superpowers, we're going to have to take some turns so we wouldn't in a helicopter. Distance, in other words, depends on context. The same is true for machine learning models. Depending on the model, we might measure the distance between our prediction and what actually happens in different ways. Exploring distance measures in machine learning. In our next lesson, we'll dive deeper into various distance measures used in machine learning, including Euclidean distance, the most common distance formula, the length of a straight line between 2 points, Manhattan distance, the city block distance useful in urban planning models, Hamming distance used to measure distance between words in natural language processing. As we explore these distance measures, we will also gain practical experience with Python lists and mathematical libraries for Python like NumPy and SciPy. These skills are not only foundational for understanding machine learning, but also essential for applying these concepts, I didn't mean to do that, in real-world data science projects. Happy coding. Representing points. In this lesson, you will learn 3 different ways to define the distance between 2 points: Euclidean distance, Manhattan distance, Hamming distance. Before diving into the distance formulas, it is first important to consider how to represent points in your code. In this exercise, we will use a list where each item in the list represents a dimension of the point. For example, the point 5, 8 could be represented in Python like this: pt1 equals a list 5, 8. Points aren't limited to just 2 dimensions. For example, a 5-dimensional point could be represented as 4, 8, 15, 16, 23. Ultimately, we want to find the distance between 2 points. We'll be writing functions that look like this: distance, which takes in list 1, 2, 3, and another list 5, 8, 9. Note that we can only find the difference between 2 points if they have the same number of dimensions. We've created a few points in script.py. Create a new point named 4D. That has 4 dimensions. Euclidean distance. Euclidean distance is the most commonly used distance formula. To find the Euclidean distance between 2 points, we first calculate the squared distance between each dimension. If we add up all of these squared differences and take the square root, we've computed the Euclidean distance. Let's take a look at the equation that represents what we just learned. Square root of a1 minus b1 squared plus a2 minus b2 squared, and so on till an minus bn squared. The image below shows a visual of Euclidean distance being calculated. Create a function named Euclidean distance. That takes 2 lists as parameters named pt1 and pt2. And the function create a variable named distance. and set it equal to 0 and return distance. After defining distance, create a for loop to iterate through the dimensions of each point. So for add the square difference between each dimension to distance. Remember in Python you can square the num. So create a for loop to iterate through the dimensions of each point. So I guess for I in range length of 0.1, add the square difference between each dimension to distance. So distance plus equals square difference. So square root of pt1 I plus pt, or it's minus, plus pt, pt2 I. Each of these needs to get squared. So I guess I technically don't need to put these in these extra parentheses, but do it just to be safe. So def Euclidean distance takes in 0.1 and 0.2. Distance starts at 0 for I in range the length of 0.1, which is fine because they have to have the same amount of dimensions. Distance plus equals the square root of 0.1 I squared plus 0.2 I squared, and then we return the distance. What is the issue? Does it need to be called num? Did I define Euclidean distance? I thought I did. Python, you can square the variable num. Defining distance, create a for loop to loop through the dimensions of each point. Add the square difference between each dimension to distance. Remember in Python you can square the variable num. What am I doing wrong? So for I in range length of 0.1, distance equals oh. So we're not doing the square root yet? When do we do the square root? So we just have 0.1 I. Did I misunderstand? Okay, I misunderstood. Okay, focus. So that 0.1 is like A1 minus 0.2. So that's B1 I. Squaring that. Okay, that makes sense. That's the distance. Outside of the for loop, take the square root of distance and return that value. Okay, yeah, this makes sense. Return the square root of the distance. So we initialize distance to 0. We add up the distance. So we add up all of these and then square root of distance. Do I need to import math or something? I forget. I thought square root was just built in. So I guess I could do okay, that's what it wanted me to do. Print the Euclidean distance between 1, 2, and 4, 0. Add another print statement which shows the Euclidean distance between 5, 4, 3 and 179. Why can't you find the difference between 2, 3, 4 and 1, 2? Because they don't have the same number of parameters or points, right? Whatever they're called, variables. Yeah. Anyway, dimensions, that's the word I was looking for. Keep it pushing. Manhattan distance. Manhattan distance is extremely similar to Euclidean distance. Rather than summing the square difference between each dimension, we instead sum the absolute value of the difference between each dimension. It's called Manhattan distance because it's similar to how you might navigate when walking city blocks. If you've ever wondered how many blocks will it take me to get from point A to point B, you've computed the Manhattan distance. The equation is shown below. The absolute value of A minus B, the absolute value of A1 minus B1 plus the absolute value of A2 minus B2, all the way up till the absolute value of AN minus BN. Note that Manhattan distance will always be greater than or equal to Euclidean distance. Take a look at the image below, visualizing Manhattan distance. Below Euclidean distance, create a function called Manhattan distance. That takes two lists named pt1 and pt2 as parameters. In the function, create a variable named distance. After defining distance, create a for loop. To loop through the dimensions of each point. So, yep. Add the absolute value of the difference between each dimension to distance. So distance plus equals abs you are done with Manhattan distance. Go ahead and find the Manhattan distance between these same points. Nice. Hamming distance. Hamming distance is another slightly different variation on the distance formula. Instead of finding the difference of each dimension, Hamming distance only cares about whether the dimensions are exactly equal. When finding the Hamming distance between 2 points, add 1 for every dimension that has different values. Hamming distance is used in spell checking algorithms. For example, the Hamming distance between the word there and the typo theet is 1. Each letter is a dimension, and each dimension has the same value except for 1. Below Manhattan distance, define your function in the same way as before. Now I have two parameters, pt1, pt2. After defining distance, create a for loop. Iterate through the dimensions of each point. If the values of each dimension are different, add 1 to distance. pt1I is it this? No. I'm brain fried, I'm sorry. That's how you would have done it. Hamming distance is done as well. Print the hamming distance. SciPy distances. Now that you've written these three distance formulas yourself, let's look at how to use them using Python's SciPy library. Euclidean distance dot Euclidean, Manhattan distance dot cityblock, hamming distance dot hamming. There are a few noteworthy details to talk about. First, SciPy implementation of Manhattan distance is called cityblock. Remember, computing Manhattan distance is like asking how many blocks away you are from a point. Second, the SciPy implementation of hamming distance will always return a number between 0 and 1. Rather than summing the numbers of differences in dimensions, this implementation sums those differences and then divides by the total number of dimensions. For example, in your implementation, the hamming distance between 1, 2, 3 and 7, 2, negative 10 would be 2. In SciPy's version, it would be 2 divided by 3. Call distance.Euclidean using the points 1, 2, and 40 as parameters. Print the result. Boom. Call distance.cityblock. Boom. Call distance.hamming. Boom. Introduction to linear regression. The purpose of machine learning is often to create a model that explains some real-world data so that we can predict what may happen next with different inputs. The simplest model that we can fit to data is a line. When we are trying to find a line that fits a set of data best, we are performing linear regression. We often want to find lines to fit data so that we can predict unknowns. For example, the market price of a house versus the square footage of a house. Can we predict how much a house will sell for given its size? The tax rate of a country versus its GDP. Can we predict taxation based on a country's GDP? The amount of chips left in the bag versus the number of chips taken. Can we predict how much longer this bag of chips will last, given how much people at this party have been eating? Imagine that we had this set of weights plotted against heights of a large set of professional baseball players. To create a linear model to explain this data, we might draw this line. Now, if we wanted to estimate the weight of a player with a height of 73 inches, we could estimate that it is around 143 pounds. A line is a rough approximation, but it allows us the ability to explain and predict variables that have a linear relationship with each other. In the rest of the lesson, we will learn how to perform linear regression. Run the code in script.py. This shows Sandra's Lemonade Stand's revenue over its first 12 months of being open. From eyeballing the graph, what do you think the revenue in month 13 would be? Enter your approximate answer as an integer in a variable called month 13. Looking like, let's say 200. Points and lines. In the last exercise, you were probably able to make a rough estimate about the next data point for Sandra's Lemonade Stand without thinking too hard about it. For our program to make the same level of guess, we have to determine what a line would look like through those data points. A line is determined by its slope and its intercept. In other words, for each point y on the line, we can say y equals mx plus b, where m is the slope and b is the intercept. Y is a given point on the y-axis, and it corresponds to a given x on the x-axis. The slope is a measure of how steep the line is, while the intercept is a measure of where the line hits the y-axis. When we perform linear regression, the goal is to get the best m and b for our data. We will determine what best means in the next exercises. We have provided a slope m and an intercept b that seems to describe the revenue data you have been given. Create a new list y that has every element in months. Multiply by m and add it to b. So y equals has every element in months. Num times m for now. Oops. Create a new list y that has every element in months, multiply by m, and add it to b. A list comprehension is probably the easiest way to do this. Plot the y values against months as a line on top of the scatter plot. Should probably put this above it then. Wait, plot the y values against months as a line on top of the scatter plot. Let's plot it with the line plt.plot months revenue. Okay, focus. Been a little bit since I used my matplotlib skills. So what we need to do, let me put this back here. So what we need to do is we need to plot these y values against the months. So if these are the months, we're going to go ahead and plot the y values against months as a line on top of the scatter plot that was plotted with the line. Okay, so we're going to make another one. Change m and b to the values that you think match the data the best. So it looks like we need a steeper slope. Let's try 10. And b looks like it's probably going to be better suited at about 50. Looks pretty good to me. I guess maybe we can make this 11, see what that's looking like. Doesn't look as good. Let's go back to 10. Feel comfortable there. I like that. Let's keep it pushing. Loss. When we think about how we can assign a slope and intercept to fit a set of points, we have to define what the best fit is. For each data point, we calculate loss, a number that measures how bad the model's, in this case the line's, prediction was. You may have seen this being referred to as error. We can think about loss as the squared distance from the point to the line. Again, loss is the squared distance from the point to the line. We do the squared distance instead of just the distance so that points above and below the line both contribute to total loss in the same way. In this example, for point A, the square distance is 9, 3 squared. For point B, the square distance is 1, 1 squared, or you could say -1 squared. So the total loss with this model is 10. If we found a line that had less loss than 10, that line would be a better model for this data. We have 3 points, 1, 5, 2, 1, and 3, 3. We are trying to find a line that produces lowest loss. We have provided you the list of x values x and y values y for these points. Find the y values that the line with weights m1 and b1 would predict for the x values given. Store these in a list called y predicted. So, y predicted. So we have 3 points. We're trying to find the line that produces lowest loss. We provided you with a list of x values x and y values y for these points. Find the y values. Find the y values that the line with the weights m1 and b1 would predict for the x values given. So brain, do your thing. So y equals mx plus b, right? So y predicted would be okay, we have 3 points 1 5 2 1 and 3 3. That's right, 1 5 2 1 3 3. We're trying to find a line that produces lowest loss. We have provided you the list of x values and y values for these points. Find the y values at the line with the weights m1 and b1. Okay, so m1 times x plus b1 provide you with a list of x values and y values for these points. Find the y values that the line with weights m1 and b1 would predict for the x values given. Store these in a list called y predicted 1. So y predicted 1 equals m1 times x plus b1 for x in x, or we could say for num in x. Or yeah, we'll do that. m1 times num plus b1 for num in x, by predicted 1. Find the y values of the line with weights m2 and b2 would predict for the x values given. Store these in a list called y predicted 2. Create a variable called total loss 1. Set it equal to 0. Then find the sum of the squared distance. So between the actual y values of the points and the y predicted 1 values by looping through the list, calculating the difference between y and y predicted 1, squaring the difference, adding it to total loss. So for I in range length, actually I don't need to do all that, I could just do for num and y. What are we doing again? We're find the sum of the squared distance between the actual y values of the points and the y predicted 1. So for num and y, find the sum of the squared distance. So sum, do squared distance be very explicit for my dumb brain right now. Find the sum of the squared distance between the actual y values. So that's y minus, we do need the index. So for I in range length of y, yi minus y predicted 1 I. So find the sum of the squared distance. So this is the distance. And we're gonna go ahead and square that hoe. And what we need is we need to find the sum of the squared distance between the actual y values of the points and the y1 predicted or y predicted 1 values by looping through the list, calculating the difference between y and y predicted. So we'll separate it. So we'll do distance equals y1 minus y predicted 1, squaring the difference. So square diff equals distance distance to the second power, adding it to total loss 1. Boom. Create a variable called total loss 2. Set equal to 0. Find the sum of the squared distance between the actual y values of the points and the y2 predicted values by looping through the list, calculating the difference between y and y predicted 2, squaring the difference, adding it to total loss 2. Print out total loss 1, total loss 2. Out of these two lines, which would you use to model the points? Probably going to go with this one, smaller loss number. Create a variable called better fit and assign it to 1 if line 1 fits the data better and 2 if line 2 fits the data better. So we're going to go ahead and create better fit equals 2. Minimizing loss. The goal of a linear regression model is to find the slope and intercept pair that minimizes loss on average across all of the data. The interactive visualization in the browser lets you try to find the line of the best fit for a random set of data points. The slider on the left controls the M, slope. The slider on the right controls the B, intercept. You can see the total loss on the right side of the visualization. I just want to say, it's insane, like how simple this stuff is. It's insane, but it's beautiful. You can see the total loss on the right side of the visualization. To get the line of best fit, we want this loss to be as small as possible. Whoa, 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 whoa. Okay. Okay. Seems like I don't think we're getting better than that. That seems pretty damn good. So you can see the total loss on the right side of the visualization. To get the best line of best fit, we want this loss to be as small as possible. To check if you got the best line, check the plot best fit box. Oh, damn. I'm off. Regardless, pretty close. Randomize a new set of points. Oh, we want, let's try 8. Okay. I mean, the B looks pretty good. Maybe it could be a little bit, oh, no, I meant to, damn. Alright. Okay. Okay. I get it though. I don't want to waste time on this. Alright, it's fine. It's not, okay, it's fine. Pretty close. Pretty close. Anyway, try to notice what method you as a human and not a computer hopefully use to minimize loss. Do you first get the slope to where it produces lowest loss and then move the intercept to where it produces lowest loss? Do you create a rough idea in your mind, but the line should be first and enter the parameters to match the image? Honestly, I went with that first option. I adjusted the slope and then I adjusted the y-intercept, and that might mainly be because of the way that these are ordered. I don't know. Gradient descent for intercept. As we try to minimize loss, we take each parameter we are changing and move it as long as we are decreasing loss. It's like we are moving down a hill and stop once we reach the bottom. The process by which we do this is called gradient descent. We move in the direction that decreases our loss the most. Gradient refers to the slope of the curve at any point. For example, let's say we are trying to find the intercept for a line. We currently have a guess of 10 for the intercept. At the point of 10 on the curve, the slope is downward. Therefore, if we increase the intercept, we should be lowering the loss, so we follow the gradient downwards. Again, let's say we're trying to find the intercept for a line. We currently have a guess of 10 for the intercept. At the point of 10 on the curve, the slope is downward. Therefore, if we increase the intercept, we should be lowering the loss, so we follow the gradient downwards. We derive these gradients using calculus. It is not crucial to understand how we arrive at the gradient equation, except your boy took calculus 3 and passed with flying colors, honors A. You know what I do. It is not crucial to understand. I probably don't understand, honestly. To find the gradient of loss as intercept changes, the formula comes out to be -2 over n, the weighted sum, I equals 1 to n, yi minus mxi plus b. N is the number of points we have in our data set. M is the current gradient guess. B is the current intercept guess. Basically, we find the sum of y value minus m times the x value plus b for all the y values and x values we have, and then we multiply the sum by a factor of -2 over n. N is the number of points we have. So first we're going to define a function called getGradient at b. That takes in a set of x values x and a set of y values y. Damn it. A slope m and an intercept b. For now, have it return b unchanged. In the getGradient at b function, we want to go through all of the x values and all of the y values and compute y minus m times x plus b for each of them. Create a variable called diff that has the sum of all these values. Instead of returning b, from the getGradient at b function, return diff. So again, what we're doing is we want to go through all of the x values and all the y values and compute y. So Ragni range for I in range length of x. Go through all diff plus equals yi minus m times xi plus b. Still in the getGradient at b function, define a variable called bgradient and set it equal to, I think we might want this above here. Can't go wrong with that. Set equal to -2 over n multiplied by diff. -2 divided by n. N is the number of points, i.e. the length of the x list. Okay. So we'll do n equals length of x. Been doing too much leak code. used to s being the input variable that I'm finding the length of for a string. So -2n times diff. And actually now we're gonna want this down at the bottom. Not there, right there. Instead of returning diff, return bgradient. Nice. Gradient descent for slope. We have a function to find the gradient of b at every point. To find the m gradient, or the way the loss changes as the slope of our line changes, we can use this formula. -2 over n, the weighted sum, I equals 1 to n, xi times yi minus mxi plus b. So again, we have a function to find the gradient of b, and again, b is the y-intercept. We have a function to find the gradient of b at every point. To find the m gradient, or the way the loss changes as the slope of our line changes, we can use this formula. Once more, n is the number of points you have in your data set. M is the current gradient guess. B is the current intercept guess. To find the m gradient, we find the sum of x value times y value minus m times x value plus b for all the y values and x values we have, and then we multiply the sum by a factor of -2 over n. N is the number of points we have. Once we have a way to calculate both the m gradient and the b gradient, we'll be able to follow both of those gradients downwards to the point of lowest loss for both the m value and the b value. Then we'll have the best m and the best b to fit our data. So again, once we have a way to calculate both the m gradient and the b gradient, we'll be able to follow both of those gradients downwards to the point of lowest loss for both the m value and the b value. Then we'll have the best m and the best b to fit our data. Define a function called getGradient at m. indentation looks crazy to me. Get gradient at m, which takes in x, y, m, b, turn m. In this function, we want to go through all of the x values and all the y values and compute x. So it's the same thing. I'm not going to copy it though, because that's cheating. I don't know why they did that to the indentation. It's making me mad. So, create a variable called diff that has the sum of all these values, return a function. So, n equals length of x for I and range. We can use n now, yeah. They did it like that, but I like doing it like this. Diff plus equals xi. Okay, I'm cheating. Xi times yi minus m times xi plus b. Add those up, and then this is the m gradient equals -2 over n times the diff. And you know, just looking at it, that looks pretty right to me. What am I doing wrong? I'm tired and I need to stop. Just stop being tired. Just shut it off. All right, what did I do wrong? Okay, think about it. Just think. Actually try. In this function, we want to go through all of the x values and all of the y values and compute x. So xi times yi minus m times xi plus b for each of them. So we did diff equals 0, n equals length of s for I in range n. Diff plus equals xi times yi minus, I guess I'll just to make it look the same as they got it, because I don't know what's going on. M gradient equals -2 divided by n times the diff, and we're returning the m gradient. Int object is not callable. Okay, I don't. Name x is not defined. I know it's not because I mistyped it. Int. Okay, where am I trying to call an int? Are these integers? X should be a list, no? If I literally copy this, we just throw another x val on here. If I were to then change this to m gradient, this to m gradient, okay, that should work. I don't understand why mine didn't work. In object, we want to go through all the x values and all the y values and compute x times, so this is x times y val minus m times x val plus b. Create a variable called diff that has the sum of all of these values and return it from the function. Oh, it wants us to return diff. Why is it saying, okay, I'm gonna hit up my boy. I'm gonna get my big brother mess you up. Oh, I'm thinking it like it's mathematics. Now I understand. So I was right. You know what? So I'm going back to what I did because we don't, extend on what we do. I just needed to add this. Bam. Define a variable called m gradient and set it equal to this and instead of so cool. Next, put it together. More like pull it together. Am I right? Now that we know how to calculate the gradient, we want to take a step in that direction. However, it's important to think about whether that step is too big or too small. We don't want to overshoot the minimum error. We can scale the size of the step by multiplying the gradient by a learning rate. To find a new b value, we would say new b equals current b minus learning rate times b gradient, where current b is our guess for what the b value is. B gradient is the gradient of the loss curve at our current guess, and learning rate is proportional to the size of the step we want to take. In a few exercises, we'll talk about the implications of a large or small learning rate. But for now, let's use a fairly small value. I'm going to read that again. Now that we know how to calculate the gradient, we want to take a step in that direction. However, it's important to think about whether that step is too big or too small. We don't want to overshoot the minimum error. We can scale the size of the step by multiplying the gradient by a learning rate. To find a new b value, we would say new b equals current b minus learning rate times b gradient, where current b is our guess for what the b value is. B gradient is the gradient of the loss curve at our current guess, and learning rate is proportional to the size of the step we want to take. In a few exercises, we'll talk about the implications of a large or small learning rate, but for now, let's use a fairly small value. Define a function called step gradient. It takes in x, y, b current, m current. This function will find the gradients at b current and m current and then return new b and m values that have been moved in that direction. For now, just return the pair b current, m current. Inside step gradient, find a gradient at b current. So and the gradient at m current using the functions defined before. Set those gradients in variables called b gradient and m gradient. Store and return these from the function. Return them as a list. Oops. Didn't mean to do that. Let's try to move the parameter values in the direction of the gradient at a rate of 0.01. Create variables called b and m. So b equals b current minus 0.01 times b gradient, and m equals m 0.01 times m gradient. Return the pair b and m from the function. We have provided Sandra's lemonade data once more. We have a guess for what we think the b and m might be. Call your function to perform one step of gradient descent. Store the results in the variables b and m. Okay, so current intercept guess. So bm equals step gradient months revenue bm, right? .355 17.783333. Convergence. How do we know when we should stop changing the parameters m and b? How will we know when our program has learned enough? To answer this, we have to define convergence. Convergence is when the loss stops changing or changes very slowly when parameters are changed. Hopefully, the algorithm will converge at the best values for the parameters m and b. Run the file. Look at the graph. This graph shows how much the parameter b changed with each iteration of a gradient descent runner. So 0 iterations, nada. At 200 iterations, the b value changed about 30. 400, it changed about 40. At 600, it changed about 45. At 1,000, it had changed about, not much, maybe like 46, 47. And 1,400, still about the same. How many iterations did it take for this program to converge? It's looking like about somewhere in the neighborhood of 900 to 1,000. Enter your answer in a variable called num iterations. I'm going to say 950. At what b value did this program converge? Oh, yeah. What b value? Yeah, we'll say like 47. Convergence equals 47. Oh, convergence b. Learning rate. We want our program to be able to iteratively learn what the best m and b values are. So for each m and b pair that we guess, we want to move them in the direction of the gradients we've calculated. But how far do we move in that direction? We have to choose a learning rate, which will determine how far down the loss curve we go. A small learning rate will take a long time to converge. You might run out of time or cycles before getting an answer. A large learning rate might skip over the best value. It might never converge. Oh no. Finding the absolute best learning rate is not necessary for training a model. You just have to find a learning rate large enough that gradient descent converges with the efficiency you need, and not so large that convergence never happens. We've imported two new lists representing how the b value changed with different learning rates. BS 0.00000001, 1,400 iterations of gradient descent on b with a learning rate of a lot of zeros and a 1. BS 01, 100 iterations of gradient descent on b with a learning rate of 0.01. Change the plot to plot BS all that. Instead of BS, does the gradient descent algorithm still converge to the same b value? Does it converge at all? So it doesn't converge. B value just keeps on going up. Look at the values on the axis. Change the plot to BS01. Whoa. So B value is not changing at all. Then it jumps. Change the plot to BS01. Unfortunately, our computers blew up after 100 iterations of this. So you'll also have to change the number of iterations to 100 instead of 1400. Oh. I already did that. I don't even really know. At each step, we know how to calculate the gradient and move it in that direction with a step size proportional to our learning rate. Now we want to make these steps until we reach convergence. We have all of the functions we have defined throughout the lesson. Now let's create a function called gradient descent that takes in x, y, learning rate, and a num iterations. For now, return -1, -1. In the function gradient descent, create variables b and m, set them both to 0. Return b and m. Update your step gradient function to take in the parameter learning rate. As the last parameter, replace the 0.01s in the calculations with learning rate. Let's go back and finish the gradient descent function. Create a loop that runs num iterations times. So for I in range num iterations. At each step, it should call step gradient. Goodness. With bmxy and learning rate. Update the values of b and m with the values step gradient returns. Outside of the function, uncomment the line that calls gradient descent. On months revenue with learning rate of 0.01 and 1,000 iterations, stores the results in variables b and m. Uncomment the lines that will plot the result to your browser. Looking pretty good. Use your functions on real data. We have constructed a way to find the best b and m values using gradient descent. Let's try this on the set of baseball players' heights and weights that we saw at the beginning of the lesson. Run the code script.py. This is a scatter plot of weight versus height, or I think that's probably weight and that's probably height. We have imported your gradient descent function, or maybe this is weight. I don't know if it's in kilograms or what. If this is kilograms and this is centimeters, I guess that makes sense. But also if this is pounds and this is inches, it could also make sense. Regardless, it's called weight versus, it doesn't matter. But it does, but it doesn't. Oh, okay, so x is the height, so it is inches, y is the weight, so that's pounds, okay. We have imported your gradient descent function, call it with parameters x, y, num iterations. So we imported the gradient descent function, call it with so I forgot to store them. Float object cannot be returned as an integer. Did I get them in the wrong order? Learning rate no matter. Why is it trying to trick me? What's the purpose? Create a list called Y predictions. Set it to be every element of X multiplied by M and add it to B. Hold up, am I in an infinite loop for some reason? What's happening? Gradient. Okay, cool. Create a list called Y predictions. Set it, so why is this short? It's annoying. Y predictions. Set it to be every element of X multiplied by M and add it to B equals so M times num plus B for num X. Easiest way to do this, so yeah, element times the slope plus intercept for element. Yep. Plot X versus Y predictions on the same plot as the scatter plot. I guess it's going slow because it's a lot, huh? See how the line's looking. I'll be patient. I wonder what that O means. Is that the shape? Oh. Honestly, wasn't expecting that. I was expecting something with a greater slope and a lower y-intercept. Does the line look right? Honestly, I would say no. I guess it doesn't look terrible. But what do I know? I'm not a computer. SciKit learn. Congratulations. You've now built a linear regression algorithm from scratch. Luckily, we don't have to do this every time we want to use linear regression. We can use Python's SciKit learn library. SciKit learn, or sklearn, is used specifically for machine learning. Inside the linear model module, there is a linear regression function we can use. So from sklearn.linearModel, import linear regression. You can first create a linear regression model and then fit it to your X and Y data. Line fitter equals linear regression. Linefitter.fit xy. The .fit method gives the model two variables that are useful to us. The linefitter.coef or coef underscore, which contains the slope, and the linefitter.intercept underscore, which contains the intercept. We can also use the .predict function to pass in X values and receive the Y values this line would predict. So Y predicted equals linefitter.predict X. Note the num iterations and the learning rate that you learned about in your own implementation have default values within SciKit-learn, so you don't need to worry about setting them specifically. We've imported a data set of soup sales data versus temperature. Run the code to see the scatter plot. Can you envision the line that would fit this data? Probably like, boom. Create an sklearn. So regression model called line fitter. So line fitter equals linear regression. Fit the line fitter object to temperature and sales. Line fitter dot fit temperature sales. Create a list called sales predict. That is the predicted sales values that line fitter would generate from the temperature list. So sales predict equals predicted sales value that line fitter would generate from the temperature list. So predicted sales values the line fitter would generate from the temperature list. So would it be where's our m though? In my head I'm thinking like m times temp plus b for temp and temperatures, but I guess that's probably not right. If I'm looking at here, y predicted equals line fitter dot predict. Oh, I don't even have to do all that. Sales predict. We simplified it, dummy. So just line fitter dot predict. Cool. And then plot sales predict against temperature as a line on the same plot as the scatter plot. If I threw a random number in there, what's gonna happen? Alright, we'll go with O. I just don't even know what it means. Does it mean orange? You gonna work? I guess I'll get this out of there. I don't know why did I do something wrong at some point? That's a letdown. I'm not gonna lie. It's a bummer, but whatever. I mean, I'm gonna. Oh, I see. Nice. Look at that line. It's a good looking line. Review. We have seen how to implement a linear regression algorithm in Python and how to use the linear regression model from SciKit Learn. We learned we can measure how well a line fits by measuring loss. The goal of linear regression is to minimize loss. To find the line of best fit, we try to find the b value, the intercept, and the m value, the slope, that minimizes loss. Convergence refers to when the parameters stop changing with each iteration. Learning rate refers to how much the parameters are changed on each iteration. We can use SciKit Learn's linear regression model to perform linear regression on a set of points. These are important tools to have in your toolkit as you continue your exploration of data science. Find another dataset, maybe in SciKit Learn's example datasets, or on Kaggle, or this one because it's Load Boston. I'm from Boston, it's perfect for me. As a starter, so try to perform linear regression on your own. If you find any cool linear correlations, make sure to share them. As a starter, we've loaded in the Boston housing dataset. We made the X values the nitrogen oxides concentration, parts per 10 million, and the Y values the housing prices. See if you can perform regression on these values. So it would be something like line fitter equals linear regression. So you load the linear regression to a fitter, then you fit it to our X values and our Y values, and then we predict line fitter dot predict X, and you save that to Y prediction, and then you plot it plt dot plot X, Y predictions. Looking pretty solid. Which of these lines seems to fit the data best? I'm going to go with A. The goal of a linear regression algorithm is to find the slope and the intercept that minimize average loss. What is the purpose of performing gradient descent? To move parameters in the direction that minimizes loss. What does the linear regression algorithm stop? When the parameters stop changing, or when does the linear regression algorithm stop? And the parameters stop changing or change very slowly. When the line goes through all the points, it never stops. Let's say we have 3 lines that produce the following average loss on our data set. Which one is the line of best fit? Line B. What is the sum of squared error between the points described by x values and y values in the line described by m and b? So y values of points, 1, -4, -7, -6. Y values of the line. So what is the sum of squared error? You're gonna make me do math in my head right now? So the sum of the squared error between the points. So the y values of the points, so 1, -4, -7, -6, and the y values of the line are 1, -3, -6, -8. It's pretty low. I'm gonna go ahead with say 3. To find the loss, square the distance. I didn't want to do all that, man. Come on, I'm tired. I'm sorry though. I guess I should have done it. If the model worked correctly, what should y new represent in the code below? If the model worked correctly, what should y new represent in the code below? I'm mad at myself for not doing that math in my head. It wasn't even that hard. But anyway, on to the next thing. If the model worked correctly, what should y new represent in the code below, right? So regression equals linear regression, regra.fit xy, y new equals regra.predict x, and if it worked correctly, y new would represent the predicted y values from a new set of x values, the same as y, the y values that x would produce on the line of best fit, the slope and intercept values of the line of best fit. Do this. If the algorithm is taking too long to converge, should you move the learning rate up or down? If it's taking too long, so we need to make the learning rate quicker, should be greater. So if we move the learning rate up, then it won't take so long to converge. Correct, gradient descent is being performed in small steps, which is making it take a long time to get to the bottom of the curve. 87, not bad, not terrible, not great, whatever. Not mad at it. So let's see, where are we at in this syllabus? So we made it through most of linear regression, really, and then there's multiple linear regression, and there's a project, and there's a bunch of stuff that I'll get back to, but for right now, I'm gonna take a young break. Peace.